Hi everyone, this is Shruthi Gowda and I'm pleased to present our work on Does thermal data make the detection systems more reliable? This is a joint work with Bahram Zonooz and Elahe Arani. Autonomous driving is a challenging and safety critical application that has to perform consistently and reliably in an ever-changing environment. Detection networks form a critical component in autonomous driving systems, but they have certain challenges as the performance degrades with variation in ambient lighting, different weather conditions, and also occlusions. The quality of the images captured degrades as the lighting decreases and is hence a problem of the camera sensors. To solve this, we explore an approach of leveraging data from a different sensor that is disparate yet complementary to the visual camera data. The regular color cameras capture visible light and are hence dependent on ambient lighting. They enjoy being highly detailed and familiar, but the quality depends on lighting, and objects occluded by glare or fog are not captured. As a new data modality, we consider thermal data from infrared cameras. IR cameras capture infrared radiation emitted by objects and is only dependent on the temperature of the object. This makes it invariant to lighting changes and other effects such as fog, smoke, and glare. On the other hand, the infrared cameras are more expensive than the regular cameras. In the example shown, pedestrians and vehicles masked due to the headlight beam are not clearly visible and hence not predicted when using RGB images. But they are very clearly seen in the thermal images. So RGB images provide detailed visual cues and thermal images offer semantic information of some missed objects. So we propose a solution to integrate these two modalities to design a comprehensive detection system. We propose a multimodal collaborative framework or MMC with two networks trained in a collaborative manner. The RGB network receives the RGB images while the thermal network receives the corresponding thermal images as the input. A collaborative training framework provides the flexibility for each network to learn complementary knowledge from the other modality without impeding its ability to learn on the modality it is trained on. To further encourage our method to explore the input feature space exhaustively and extract all the semantic information into the learned representations, we apply an auxiliary task for reconstructing the inputs. The auxiliary task network takes in the features from the intermediate layers of the encoders and aims to reconstruct the input image via the decoders for reconstruction purposes. For each network is trained with supervised detection loss and the mimicry loss. We use Kullberg-Lieber divergence. For the other variants of MMC, we use an additional reconstruction loss. In self-reconstruction, the encoder and the decoder are from the same modality, and for cross-reconstruction, it is of a different modality. For example, the intermediate features of the RGB network are sent to reconstruct the thermal input image and vice versa. We also compare our method with other techniques. In fusion technique, input fusion concatenates the visual and thermal image pairs before feeding to the network, while feature fusion concatenates features from two encoders, one receiving RGB and one thermal. Inspired by the recent ideas of style transfer from one type of image to another, we also explored the idea of transferring the style of thermal modality onto the visual modality. The table shows the results of our proposed MMC approach for cased and FLIR datasets along with the results of baseline, fusion, and stylization models for comparison. The RGB test set is further divided into day and night images to analyze the effect of thermal images during different times of the day. The focus here is on RGB test data as these are the images that are used in the end application. So, the RGB plus thermal baseline shows that training with a combination of RGB and thermal data does improve accuracy over just using RGB images on nighttime images. MMC techniques collaboratively train two networks and are the only method to show improvements on day, night, and overall test set for both the datasets. MMC outperforms on nighttime images, and MMC with reconstruction achieves the best day result for the daytime images. Going back to this example, we can now observe that the MMC approach makes accurate predictions, thus helping autonomous driving systems in making timely decisions. Autonomous driving systems need to be robust to ever-changing environments. To test the performance of the detection networks on different challenging scenarios such as varying weather conditions, sensors, and other external influences, we create a data set by adding natural corruptions to the RGB test set. We apply 15 different corruptions ranging from noise, blur, weather, and digital effects. The heat maps show the accuracy results for 15 different corruptions on cased and flared dataset respectively. MMC methods perform better than baseline on all the corruptions for both the datasets. Deep neural networks are shown to be vulnerable to adversarial attacks, which are carefully crafted and imperceptible noise added to the input image to fool the network. These can have disastrous consequences for security critical applications like autonomous driving, while, for example, can be fooled to consider a stop sign as a 100 km/h speed limit that can lead to untimely decisions. We consider the projected gradient descent, or the PGD, which is a first-order adversary utilizing the local first-order information about the network to generate an adversarial perturbation within an epsilon bound. The PGD here we perform using both classification and regression loss. We perform a targeted PGD attack by hiding the class person and car respectively. Here, the MMC proves to be more robust across varying attack strengths as shown in the graph. So, along with the benefits of adding the thermal data, we also show the overheads of using the thermal imaging system. Thermal cameras are more expensive than their visual counterparts and hence can prove a constraint. Also, we highlight cases where thermal provides missing information as shown in figure in the left, where pedestrians crossing the road are missed in RGB but detected with the thermal data. But in the example in the right, we see cases where RGB is self-sufficient. So, in applications where safety is not the utmost criteria, thermal might actually add more overhead and cost. On the other hand, in autonomous driving systems, where even a single extra detection can help avoid a disastrous accident, thermal data proves to be more beneficial. So in overall, we provide a holistic picture by highlighting both the benefits and overheads of using thermal data and hope this work is beneficial to the community. Thank you very much.